Hello! In this question, we're looking at function composition, but not quite in the way that you know it. See, normally you would get a function, and then you have to compose it with another function, and then you find the resulting one. But in this case, we're given the composition already, and have to try and find the original function. So that's what these three questions are themed on. One important thing to note is the wording used. In part A we have state, but in part B and part C we have find. So this suggests that A will likely be much easier to just state it, you don't really have to show any working out, whereas B and C will involve a bit more effort. Another thing to note is that in part A and B we want specific functions, but in part C we only want specific values, so we may not have to find the full function for part C. The first part is fairly simple. We can see that the composition of f with itself is x squared. So this means that f of x is probably of the form some x to the power of a. And that would mean that if we compose it with itself, so we have f of x, that would be x to the power of a to the power of a. And well, this is clearly just x to the a squared. And we know that this is equal to x squared. So this gives us a squared is equal to 2. Or rather, a is equal to plus or minus the square root of 2. So that just gives fx, it could be equal to x to the power of root 2, or it could be equal to x to the power of minus root 2. And these are both defined for x is greater than 0. Part B is a bit trickier. We can start by noticing that the highest power of the polynomial is 4. So this means it's likely that the highest power of gx is 2. If we try a solution of the form gx is equal to x squared plus some ax plus some b, then we end up with g of x is equal to x squared plus ax plus b squared plus a x squared plus ax plus b plus b. So we've just replaced the x's with the function itself. Now I'm not going to go through all of the working, but you should end up getting x to the power of 4 plus 2ax to the power of 3 plus, and then we open the brackets, a squared plus 2b plus ax squared, 2ab plus a squared x, and b squared plus ab plus b as the constant term. For now, we can just generally ignore the later terms and then focus on just this very simple one, this 2a x cubed. Because we know that this is supposed to be 4, so 2a is 4, so this means that a is 2. Now we can plug a equals 2 back into this equation, and we end up with 4 plus 2b plus 2, so that's 6 plus 2b, is equal to this term here, which is minus 2. So 6 plus 2b is equal to minus 2, or rather, 2b is equal to minus 8, which gives b as being minus 4. And you may be like, okay, we're done, but we have to make sure this is actually the form we want, so that the polynomial is what we expect it to be. And to do that, we have to check the last two coefficients. Plugging this in, we get 2 times 2 times minus 4 plus 4 is equal to 12. We just need to check that this works. So that's minus 16 plus 4. So yeah, that does check out. And checking the constant term, we want 16 plus 2 times minus 4 plus minus 4 to be equal to 4. And well, this is 16 minus 8 minus 4. And yeah, that's 4. It checks out. So we can say that one possible gx is gx equal to x squared plus 2x minus 4. Part C is a bit of a curveball, because previously we've had to find the full function, whereas here we only want possible values, so all possible values that h of minus a half can take. And if we were to find every single function h of x that could possibly exist, it would probably take a while, And even then, we'd have to check them all to make sure that h of minus a half isn't magically a different value in them. So we probably need a bit of a different approach here. We're going to start by letting h of minus a half be equal to some value. Let's call it a. And then we can actually apply the function to both sides. And then we get h of minus a half is h of a. And we can work out h of minus a half. And, well, we just plug it in here. So minus a half squared, that's a quarter, and then plus a quarter. So we have a half is equal to h of a. Now we apply the function h a second time, and we get h of the half is equal to h of a. And we know that this is equal to a squared plus a quarter. From this point, we can't really do too much, but I am interested to know what h of a half could be. So let's make h of a half be equal to b. So what is h of a half if we apply this to both sides? Well, plugging a half into here would give the same answer. It would give a half is equal to h of b. And now when we apply h again, we get h of a half is equal to h of b. And this is equal to b squared plus a quarter. Now you're probably thinking, well, okay, why did you just do that? That's the same as what you did before. But as it turns out, we have a h of a half here, and we have a h of a half here. So we have, taking both sides, b is equal to b squared plus a quarter. And this is just a quadratic. So we can rearrange this for 4b squared minus 4b plus 1 is equal to 0. Factorizing, we find that this is 2b minus 1 squared. So b must be a half. And see, now we're getting somewhere because we know that h of a half on this left-hand side here is equal to a half. And now using both sides, we get that a half is equal to a squared plus a quarter. Or more accurately, a squared is equal to a quarter. And this gives that a is equal to plus or minus a half and can take no other values. So these are all the possible values that h of minus a half could be.